Hi everyone and welcome back to PrepFusion. I'm Anish and today we'll start with the lecture 23 of our machines chapter, machine subject, right? So today we will do the assignment 8 solutions, that is the solutions of the three-phase transformers. So let's start with this one. What is the phase displacement between the primary and secondary voltage for this three-phase star to delta transformer? Okay. Now just these kind of questions will come in ESC only, where they will not mention what is a dot. So these kind of controversial questions will come in ESC only. In gate they will actually tell you which is dot, which is not dot. Okay, it will be mentioned, but in ESC they don't care. That's why they don't mention. So I took this question just in case if the dot is not given. So what you'll do, by default you'll assume the output terminals to be the dot, and for input, for primary this is for the output, this is for the secondary, and this is for the input, you will assume the input terminals to be the dot. Got it? So if nothing is mentioned, if nothing mentioned, by default you will assume the uh, output terminals to be dot. Why? Because if you remember, right, my single phase transformer, we thought the input current was coming here, so that's why we assumed this dot, and in output the current was leaving, so that's why we assumed this as dot. If you remember, for a single phase transformer, same thing, output terminal to be dot in the secondary side, basically where the load will be connected, secondary side, and the input terminal to be dot in the primary side. Okay, so what we can do is, yeah, same thing we will do. So we will copy this circuit. There will be a phase shift of 30 because it is star delta, or okay, there will be a phase shift of 30. Will it be leading or lagging, that I need to check. So input terminals are somewhere, sorry, supply terminals are here, right? These are my supply terminals. So the dot will be connected here. Okay, so dot will be connected here. These are my input terminals, and output terminals are here, right? These are my output terminals, correct, from which I will take the output. So these are my output terminals and these are my input terminals. Okay, so I have done the dot. Now let me find out the phase difference. So what is VAB here? So this is just a neutral, right? This is just a neutral. This one is just a neutral. So this will be plus minus VA here, and this will be plus minus VB. So what is my VAB basically? How do I calculate my VAB? So my VAB will be, okay, sorry, this is okay, sorry, this is not ABC, right? This is ABC actually, sorry. This is not possible because this is already shorted. So these are my input terminals, sorry, then though things will change. This will be my ABC basically. Then oh, sorry, this is strong, right? This will not be ABC actually. ABC, this will not be, this will be my ABC. It is not possible for that to be the ABC, sorry. So then, right, this will be basically dot will come here, dot will come here, dot will come here, dot will come here. So this will be plus minus VA plus minus VB plus minus VC. Okay, and this is plus minus VA here, plus minus VB here, plus minus VC here. Okay, so what I can say is, what is my VAB? So my VAB will be basically so it is okay, it is plus VA minus VB. Okay, so it is basically like root 3 into VA. It leads the phase voltage VA by 30 degrees. What about V small ab? So V small ab, if I see, it is simply plus minus VA only, right? Plus VA only. Okay, so it is basically VA angle of 0, right? So what is the phase difference between the star and delta? What is the phase difference between primary and secondary? So my here, right, bit of confusion is there. So my primary leads the secondary by 30 degrees, so it will be 30 degrees, right? 30 degree leading. Primary leads the secondary by 30 degrees, so it will be 30 degrees leading. Okay, so bit of confusion is there. Okay, if star side of the star delta transformer in the figure is excited by a negative sequence voltage, then what are they asking? Negative sequence voltage. So what does negative sequence voltage means? Remember, negative sequence means the phase sequence has changed now. So if it is negative sequence, I have not mentioned this previously. Positive sequence, generally positive sequence means the phase sequence will be A, B, C. If it is negative phase sequence, everything changes. It is A, C, B. That means basically, that means what, like whatever we know, right? For positive phase sequence, we know that my voltage will be VA angle 0, then it will be VA angle, so the other voltage, right, it will be VB angle 120, and it will be VC angle minus of 120. Okay, so what about negative phase sequence? So negative phase sequence, right? If it is negative phase sequence, that basically means, that this will be, I will start with A only, but the next voltage will be VC, it will not be VB anymore, and the next voltage will be VC angle of minus 120 degrees. So not VC, sorry, VB angle minus 120. So that is the difference here. So we have to be careful here. So now what are they asking? Then VAB leads VAB by 60. All these are asking, right? So how will I write? So I will first calculate what is VAB. What is VAB here? VAB. So I will copy this circuit. Remember, this is my phasor now. These are my phasors, not this one. So I will draw my phasors actually. So before that, let me copy the circuit as well. Let me copy the diagram as well. If I copy the diagram, this is my diagram, right? And what about the phasors? So my VA will be in the same direction, capital VA will be in the same direction, but in the clockwise now, VC will come, VB will not come. Why? Because here, right, VC leads by 120 degrees. That's why now VC leads VA by 120 degrees. So okay, VC will lead VA by 120 degrees. Am I correct here? Oh, sorry. I made a blunder here. This should have been minus 120, right? Sorry. I made a blunder. This should have been minus 120. This should be plus 120. This should be then minus 120. Sorry about that. I know you guys are screaming in the comments. This will be plus 120. Okay. Sorry about that. So that's why VC will lag by 120. So VC will come here. Previously VB was used to come here because VB used to lag by 120, right? Now VC lags by 120 because the phase sequence has changed. What is phase sequence? I have described in the basics of three phase. In the starting of previous lecture also, I discussed a bit about phase sequence. Okay, so this will be VC here and VB will be here. Okay, so this is VA, VB, VC. Now what is VAB? VAB, if I see, this is plus minus and this is plus minus, correct? So basically it is plus of VA minus of capital VB. Okay, so plus VA minus of VB, so minus of VB will be somewhere here. So basically my VAB will be somewhere here, that is it lags the phase voltage. Now it actually lags, it does not lead the VA, it lags the VA. Okay, so this is 30-degree lagging here. What about the other side, small VAB? So small VAB, again the same thing, right? It follows the, basically it follows the negative phase sequence again. So this will be VA, VC, VB. Okay, so okay, so now what is my VAB? VAB is this value, right? It is VA only, right? If I assume, okay, they have not mentioned what are the phase voltages. Okay, they should have actually mentioned. Whatever, it will be plus VA only. It will be plus VA. So this will be plus VA, basically. So basically this, right, they should have mentioned actually. This should have been mentioned that this is coil A. So it is plus VA. So V small AB is plus VA only, right? Plus VA only. So it is in the same direction as VA. This is my V small AB. Okay, so it is in the same direction as VA. So what is the phase difference? 30 degrees. So my capital VAB lags small VAB by 30 degrees, or I can say my small VAB leads capital VAB by 30 degrees. But here capital VAB is there, so capital VAB lags small VAB by 30 degrees. So option C will be the correct answer here. Capital VAB lags small VAB by 30 degrees. This will be the correct answer. Okay, so let's now try to solve the next question. Next question is this one. In the given figure, a three-phase transformer connection is partially shown. What will be the voltage reading? Okay, what will be the voltage reading? That is what they are asking. So, okay, so it is 400 volt line to line here. So it is a star connection only. So if it is 400 volt line to line here, so what will be the phase voltage here? It will be 400 by root 3. Okay. So basically my capital VA will be 400 magnitude, I'm only talking about magnitude, will be 400 by root 3. Okay, now I know that this acts as a transformer only for the coils. So what will be my small VA, magnitude of small VA? Phase difference I will discuss later on. Let's first discuss about the magnitude. So magnitude of small VA upon magnitude of capital VA will be the turns ratio. So it is 75 divided by 100. I know magnitude of capital VA, that is 400 divided by root 3. So magnitude of small VA will be equals to 75 divided by 100 into 400 divided by root 3. Okay, so this will be basically 300 divided by root 3. So it is 100 root 3. Okay, it is 100 root 3. that is what this magnitude of V is. Did I use any formula that x 1 by x? No, that is there, that was there because many students want the formula. Sir, formula de do, formula de do. Did I use any formula here? No, nothing formula. Still I am able to find out the output voltage without a single formula. Okay, so that's why I recommend, right? That's what I recommend as well, because in examination hall you won't be able to take all the formulas. Okay, so yeah, that is magnitude of Va. Now let's discuss about phase difference. So what will be the voltmeter reading? So this voltmeter reading, right, if nothing is mentioned, assumption is it is like it is what do you say, it is positive phase sequence only. So voltmeter reading is voltage between these 2 points. So if I apply a KVL here, if I apply KVL, okay, I have to apply KVL. How will I apply the KVL? That is what I'm thinking. Okay, it's like a long KVL. Okay, the KVL is a bit long. Okay, so this will be like, okay, let me write down the voltages. So this will be plus minus VA. This will be like, okay, this will be plus minus VB. This will be plus minus VC. So my KVL will be somewhat like this. This will be plus minus plus the voltmeter reading V. So we'll start from, I'll start from here, go here, then go here, then again go here, and then end it here. Okay, so basically what is the flow? Flow is like this. First I will encounter A coil, then I'm encountering the positive side of the B coil, then I'm encountering the negative side of the C coil. So basically it is equals to my minus of V. I'm just applying simple KVL, minus of V plus of VA plus of VB, then minus of VC equals to 0. So V equals to VA plus VB minus VC. So this will be equals to VA is this magnitude phase 0 degree, right? It is phase sequence ABC, so it will be angle 0. This will be plus magnitude will be same, but it will provide a phase shift of minus 120. Angle will be minus 120 and subtraction of this value minus 100 root 3 plus 120. Okay, so what will be the value here? That is what we are trying to identify. So how do I identify this thing? Okay, so what I can do, I can again apply the same thing, right? So I have three phasors. One is at angle 100, root 3 angle of 0. Another one is at angle minus 120, right? Minus 120, minus 120. So it is in the clockwise direction. Minus 120 is here. 100 root 3 minus 120. Another one is minus 100 root 3 plus 120. So if 100 root 3 plus 120 is where, 100 root 3 plus 120 will be somewhere here, right? This will be 100 root 3 plus 120. Now I have to phase opposite. Okay, I will oppose it later. Give me 1 second. So let me find out the equivalent of these two, right? Because these two are simply added. If you see, these two are simply added. So if these two are added simply, so here what will happen? What is the phase? Like these are magnitude are same and angle between them is 120, right? So what will happen? Again the same concept, right? Again the resultant will come in the bisector. So the resultant will be 2 into 100 root 3, the magnitude, into the cos of angle between them. What is the cos of angle between them? It is cos of 120, right? Cos of 120. Okay, magnitude of cos of 120, because cos 120 will be something negative. Okay, so cos of 120. Just concerned about the magnitude. Okay, so it is half only. So this will come out to be 100 root 3 only. So this angle is actually 60 degrees, right? It will be coming at half and the other parts will be cancelled. What about this one? So if I actually oppose it, right? So this whole angle is 180, right? This whole angle is 180. I know this angle is 120. So this angle is also 60. So if I oppose it, it is actually lying in the same direction as the resultant of these two addition. Okay, so basically what is happening, this is minus of 100 root 3 minus 120. Okay, so basically I will add these two values, so they are in the same phase, so ultimately my resultant will come out to be 200 root 3. I am doing vector addition, simple to vector addition. If you don't know vector addition, please go and search how to do vector addition in class 11 and 12. Okay, so although in phases as well, in my AC analysis, there I have also have described how to do vector addition, vector formulas also I have described there. Okay, so this will be 200 root 3. Angle will be what? Same angle, right? This is minus 120. This angle is also minus 120 only. Sorry, not minus 120. Sorry, this angle is basically minus 60 from the reference, right? Minus 60 from the reference. Okay, so this angle will be minus 60 from the reference. Okay, so what have they asked actually? They have asked what will be the voltmeter reading, because I don't care about the phase, I care about the voltmeter reading. So voltmeter will read basically the magnitude only, right? Voltmeter will not be able to read the phase, so voltmeter will read the magnitude only. So voltmeter reading will be magnitude of 200 root 3 angle 60. So this will be 200 root 3 volts. Okay, so this will be the answer. So let's now solve the next question. Two single phase 1:1 transformers with turns ratio 1 and 2. So turns ratio of, okay, two 1:1 two transformers with turns ratio of 1 and 2 respectively are connected to a three phase supply as shown in the figure. Okay, they are connected to a three phase supply and their turns ratio individually are 1:1 as shown in the figure. What will be the reading of voltmeter V2? So basically they are asking me what will be the reading of this voltmeter V2. Okay, how will I measure the voltage voltmeter V2? I know here I have a voltage of 100 angle 0. So here what will be the voltage? Same, right? Because it is an isolation transformer and voltage ratio will be same in coils. So coil voltages will just work as a single phase transformer. That is what we have discussed in three phase transformer, right? So here the value will be 100 angle 0 only. This will not change. Okay, this will be plus, this will be minus. What is the value here? So here this is 100 angle minus 120. Here also the value will be 100 angle minus 120 only. Okay, so this value will be 100 angle minus 120 only. Okay, so this will come. Okay, okay, sorry, the turns ratio is given here, right? 1:2. Sorry, I missed the turns ratio. It is 1:2. So for the below transformer, the turns ratio is 1:2. So if it is here 100 angle minus 120, here it will be 200 angle minus 120. So this value will be 200 angle minus 120. Okay, now what you have to do, this is plus, this is minus, just simply add the voltages, just simply use KVL, right? Simply use KVL. So basically if let's assume that this voltage is plus minus V2, then I will apply the KVL like this, that this will be minus V2 plus 100 angle 0 plus 200 angle minus 120. Okay, so this will be 0 basically. So from here I can write what is my V2. So V2 is equals to this will be 100 angle 0 plus 200 angle minus 120. So we can apply, this will be 100 plus 200 into cos of minus 120 plus sine of minus 120. So V2 will be equals to 120 cos minus 0.5. So 100 plus 200 minus 0.5 minus sine of minus 120 will be, I guess, minus 0.86, right? Just hold on. 120 minus sine of this will be minus 0.866 J. sorry, j was there, right? I forgot to write the j here. So this value will be, basically this value will be 100 will get cancelled. This value will be minus, this is root 3 by 2, so this will be 100 j minus 100 root 3. Okay, so what will be the magnitude? Basically magnitude will be 100 into root 3. It is 0.866, sorry, 1.732. So magnitude, so voltmeter reading will be V2, magnitude of V2 will be 172, right? So 100 into root 3, that is 173.2 volts. Okay, 173.2 volts. This will be the magnitude basically. This will be the answer. Now let's solve the next question. A three-phase transformer with YD connection has an input voltage of 1000 and provides output line voltage of 1000 volts. If the primary and secondary are reconnected as delta and zigzag respectively, the same input voltage applied, what will be the output line voltages? Okay, we will not try to use any formulas here. My effort will be not try to use any formulas. So if my transformer first initially is a star to delta transformer, okay, I have my transformer here, so it is a star to delta transformer. So my transformer is a star to delta transformer. So if it's a star to delta transformers, let's assume that the turns ratio here is N1 N2, and I know in the high voltage side, the, let me write here NHV and NLV, that also works, anything works, right? Anything, any notation works. I will write N1 N2 only. High voltage side the voltage is 1000, low voltage side the voltage is 100. Okay, so high voltage side the voltage is 1000, low voltage side the voltage is 100. Now what I need to do is I need to find out this turns ratio. It is a star delta transformer, so this is line voltage, right? 1000 voltage, if nothing is mentioned, it is line voltage, it is 9 voltage. So what is the phase voltage? What is the coil voltage? So coil voltage for the high voltage side, so coil voltage for the high voltage side will be 1000 divided by root 3. So this is the coil voltage for the high voltage side. I will write here coil voltage for HV side, okay, divided by the coil voltage of the low LV side. What is the coil voltage here, right? The LV side is delta connected, so line and phase voltage are same, so this will be 100 only. That is given as the ratio of turns ratio, N1 by N2. Okay, so from here I can simply find out the turns ratio. So N1 by N2 comes out to be 10 divided by root 3. That is what N1 by N2 comes out to be. Okay, what is happening in zigzag? What is happening in zigzag? So in zigzag, if you see, I have my transformer in what, it is delta zigzag, right? If the what will be the output line voltage of DZ connected transformer? So if it is delta connected now, so if it is delta connected, input line voltage is still 1000 volts, it is DZ. So if you remember that the line voltage in zigzag was actually 3 by 2 times the line voltage, right? Sorry, phase voltage. If you remember, if I go back, so this formula you have to, like, you can remember, because how many things will you derive, right? This derivation will be bit lengthy. So this we derived here actually, right? Here if we see that it was 3 by 2 of the phase voltage. So that is what we will do right here. That is what we will do. So okay, 3 by 2 of phase voltage, that is the coil voltage, right? Still the turns ratio will be same only, N1 and 2. The turns ratio won't change, because they are telling you that the windings are reconnected as delta zigzag. So transformer is same, turns ratio is same, just they are reconnected as delta and zigzag. Okay, so what is the phase voltage here in the high voltage side? It will be 1000, correct? Phase voltage in the high voltage side will be 1000, that is coil voltage also will be 1000. In the right hand side, what is the uh, phase voltage? So in the right hand side, the phase voltage VA is 2 by 3 of VAB, right? Because I know the line voltage, right? On the right hand side, I have information about the line voltage of the right hand side. What is the line voltage at the right hand side? The line voltage at the right hand side is basically this value, right? 100. Okay, sorry, I have to find out the line voltage. Okay, sorry, I have to find out the line voltage. Okay, so this is this is VA basically. So uh, this will be 2 by 3 VAB. That is what I need to find out. 2 by 3 VAB. Sorry, I made a mistake. So basically we have to find out this VAB, right? The ratio of the coil voltages, that is VA is the coil voltage of the secondary and this is the coil voltage of the primary, will be equals to basically the turns ratio N1 by N2. Okay, so from here I can directly say what is my VAB. So it is N1 by N2 is 10 by root 3, so that root 3 will go there by 10 into 3 by 2 into 1000. So 100, 50, 150, 150 root 3. So your VAB comes out to be 150 root 3. Okay, I hope you have understood this very basic point, right? This is your VAB. Okay, yeah, this is your VAB. So what is VAB in absolute numbers? It will be 150 into root 3, so 259.8. Let me go over this question again. I believe there might be a bit of doubt. So initially I had a 3-phase transformer with star delta connection as shown. Input line is 1000 volt. So line voltage, always whenever they are giving voltage, it will be always line voltage unless and until specified. Provides output line voltage of 100 volts. So this is the connection diagram. Star delta, input is 1000, output is 100 volts. Okay, great. Because here delta is the low voltage side, that's why the delta came at the low voltage side. Okay, if the primary and secondary are reconnected as delta and zigzag, if the primary and secondary are reconnected as delta and zigzag, okay, that is DZ transformer. So this time D is capital. If you see, D is capital and Z is small. Here as well, Y is capital, D is small. That's why D will be coming at the high voltage side and zigzag will come in the low voltage side. Now they are asking what will be the, for the same input applied voltage 1000 volt, what will be the output line voltage. So I know I from this I will easily be able to find out the turns ratio. As soon as I have found out the turns ratio, this unfortunately only one thing I will tell you to remember, this one. It's very good if you remember, this will be very helpful, right? The line voltage on a zigzag connection will be 3 by 2 times of the phase voltage, that's it, or the coil voltage. Okay, now I will replace here coil voltage will be equal to 2 by 3 of the line voltage. Okay, so it is 2 by 3 of the line voltage, this is 1000 volts, that is equals to N1 by N2, that is equals to N1 by N2. Okay, so my VAB equals to root 3 by 10. So like this, right? I have just taken this N2 there, N1 here. This is just the coil voltage ratio. So N2 by N1, so that is this is N2 by N1 is basically inverse of this 10 by root 3, root 3 by 10. So this will be root 3 by 10 into 3 by 2. Okay, 3 by 2 is this value into VA. So not VA into the 1000 will be still here. So VAB will go in this side. Okay, left hand side. So from here I can directly calculate that VAB will be 259.8 volts. So this is how you will solve the question. Mostly questions will be very easy. You don't have to draw a connection diagram, all those things, right? Question will be very easy mostly. Okay, so let's solve this next question. So this question actually is from power system analysis. So in power system analysis we will go more in depth for this question. Okay, one thing you have to keep in mind, whenever you have a 3-phase transformer or any transformer for a matter of fact, that the per unit impedance on the secondary and the per unit impedance on the primary will be same. This I think we have derived as well previously. Okay, and we will again derive it in the power system analysis subject. Okay, so the per unit impedance is same. So if the per unit impedance is same, then from here I can directly derive, right? So secondary is Z2 upon Z base, correct? Z base of the secondary, Z base of the secondary might be different, right? Might be different, and it will be Z2 dash, that is referred to the primary. This Z2 is referred to the primary upon Z base 1, right? Because this impedance is referred to the primary, so the effect will be same, right? It is just Z2 referred to primary divided by the Z base, so the per unit will be same, but this absolute value will change. Okay, don't worry if you don't know this relation, we will derive this in the power system analysis. So Z2 is given to me as 4 ohms. What is Z base? Z base is basically kV square, kV2 whole square upon MVA, right? This we have already discussed, or you can derive it. I'm not deriving it anymore, but this we have already previously discussed, right? If you remember, it was kV2 whole square upon MVA. MVA2, basically MVA is same only, MVA on the secondary and primary is same, and this will be Z2 dash upon kV1 whole square, kV1 whole square upon MVA 1. Okay, so here, right, kV2 and kV1 are always with respect to line voltages. We will always write with respect to the line voltage because the impedance is connected in the line only. Okay, that's why, because here the impedance is connected on the line only. So this will be 4 upon kV2 whole square, it is 220 whole square into MVA. MVA is same only, right? So MVA on the secondary and MVA on the primary is same because transformer MVA is conserved, so it does not change. This will be equals to this into 110 whole square, sorry for the noise, background noise, into Z2 dash. So from here I can directly say what is my Z2 dash. So my Z2 dash will be equals to 4 divided by 4, that is 1 ohms. Okay, so 1 ohms is present in the option D. I know there is bit of controversy in this question. This will be clear to you when we will move in the power system analysis. Okay, so now let's solve this next question. In this question, what we have to do, a balanced positive sequence 3-phase AC voltage source is connected to a balanced star connected load through star delta transformer. So it is a star delta transformer. This is a balanced 3-phase star connected network, and this is a three-phase load star connected. Okay, so it is star to delta. If we see, it is star to delta. How can I say it is star to delta? Because 3 points are shorted here and delta is here. Okay, because if you see, this point is connected here, then this point is connected here, then this point is connected here, so it is like a delta connection. What are they asking? The line to line voltage is 230 volt on the star side. So here, right, line to line voltage is 230 volts. Line to line, I'm talking about line to line. So line to line, right, this value is 230 volts. Okay, and 115 volts in the delta side. So here the line to line voltage is 115 volts. Okay, if the magnetizing current is neglected, is is 100. So that is here, right, the current source, sorry, is means the secondary current is 100 amperes. What are they asking then? Then they are asking what is the value of IP current. Okay, so we have to find out the value of IP current. So actually this is a kind of a good question. What will be the value of IP current? I know IS, what will be the value of IP? So IS and IP also will follow the same relation, right? So previously what we had discussed, that coil voltage of 1 upon coil voltage of 2 will be equals to N1 divided by N2. Okay, coil voltage of 1 divided by coil voltage of 2 will be equals to N1 divided by N2. And also the coil current of 1 upon the coil current of 2 will be just the inverse of this. will be just the inverse of this. It will be n2 upon n1. That's it. Okay, it will just be inverse of this. Okay, so what we can do is I will find out this ratio because voltages are given to me, and I will put it here. That will work. So here if I see, the coil current and the line current are not same because it is delta connected. Keep this in mind. Okay, we will fix this. So let's first of all let's calculate this n1 upon n2, right? So I know what is the coil voltage on the high voltage side. It is 230 divided by root 3. It is not 230 because it is a line voltage here. Coil voltage will be divided by root 3 because it is star connected. So this I will solve. 230 divided by root 3 divided by here, right? In the secondary, what is happening? 115 volts. 115 volts. So this will be 115 volts. This will be equals to n1 divided by n2. Okay. So n1 divided by n2 comes out, the ratio comes out, n1 divided by n2 comes out to be 2 root 3. Okay. What about here? So what is the coil current 1? Coil current 1 is same as IP, right? It is same as IP. So this current and the coil current both are same series. Okay, it is star connected. So this will be IP only. IP magnitude, I am only talking about magnitude, not talking about phase right now. Okay, we can calculate phase as well. Can we? Yes, because I know how much phase difference it will provide. Okay, they are actually they are asking the phase as well. That is actually pretty good. They are actually asking the phase. Okay, so if they are asking the phase, okay, what will the phase? So I know in the delta side what happens, the line current lags the phase current by 30 degrees. Okay, I will come to that later. Let me first of all at least discuss about the magnitude. Okay, let me discuss about the magnitude. There are other ways to solve the magnitude as well. I will discuss about that. So magnitude of IP upon, now in the secondary, right? In the secondary, if I see that IS and this coil current is not same. So this coil current will be what? IS by root 3. Okay, this we have learned in the previous lecture and in the basics of basis of three phase, right? Because it is delta connected. So this will be IS divided by root 3. So this will be magnitude of IS divided by root 3. Okay, so this will be N2 divided by N1. So okay, so what is N2 divided by N1? It will be inverse, right? 1 by 2 root 3, and this root 3 is there. So this root 3 basically it is IP magnitude by IS magnitude into root 3 equals to 1 by 2 root 3. Okay, because it is inverse, right? Yes. So actually my IP magnitude of IP comes out to be IS by 6. Okay, IS is 100. Okay, something have I done wrong? Okay, this will be IS by root 3 only. This will be, this current will be more, right? I guess line current will be more than the phase current. Yes, root 3. Okay, 100 volts. Oh, sorry, what am I doing? This is 2 by root 3. 2 by root 3, sorry. So this will be basically root 3 by 2. So this will come out to be root 3 will get cancelled. So it will be is by 2, that is 50. So magnitude is 50, that is fine. What about the phase? So I can calculate the phase basically. What do I know? I know in case of a delta, the line current for delta, right? For delta, the line current will lag the phase current by 30 degrees if it is obviously balanced. Of course, all these are for balanced load. If it is not balanced, nothing will follow. Okay. One more thing I know, that there will not be any phase shift between the high voltage and the low voltage winding, between the coil current, right? There will not be any phase shift. So this is the point 1. Point 2 is there will not be any phase shift between the coil currents. There will not be any phase shift between the coil currents. So what we can say is that what is the line to line in the secondary. So this is basically, this statement basically means that is will lead the lag the coil current of the delta by 30 degrees. So basically my is will lag the coil current of the delta by 30 degrees. So is will be minus 30 with respect to the delta current of the phase, right? And what is the phase difference between the delta current of the phase and the star current of the phase? So it is 0 degree. So basically I can say is will lag, like if I go from is to ip, because ip, the phase current and the coil current are same, right? Ip, the same current is flowing through the coil and through the phase. So basically I can safely say with respect to, so is is angle 0. Okay, is is angle 0. So if is is angle 0 and I know is lags ip by 30 degrees, so the other way also I can say that ip leads is by 30 degrees. ip leads is by 30 degrees. Okay, so this is what we say. So this will be 50 angle plus 30. Okay, 50 angle plus 30 will be present in option A. So for phase angle, right, actually you don't have any other method. You have to solve using this only. For phase angle, you have to solve using this. Now method 2, what if they would have asked only the magnitude? So method 2 will work. What if they would have only asked for magnitude? So this was the method 1, and obviously you have to anyways understand this part. This part will be common to both methods, right? This part will be common to both the methods, because you will not be able to identify the phase otherwise using the other method. Other method is using kVA, equating the kV, right? Equating the VA rating, volt ampere rating. So I know basically the kVA of the primary side will be same as kVA of the secondary side. Has to be, right? kVA is conserved. So in the primary side, what is the three phase power? It is root 3 into VL1 into IL1, I line to line 1. And in the secondary side, it is root 3 into VL2 into IL2. So what is the line voltage in the primary side? Line voltage in the primary side is 230 volt. They have given to me. So it will be 230 volts here into the current is line current and the phase current is same for star connected load. It will be IP. Okay, magnitude of IP, because we were only discussing about the magnitude. This is equals to here VL2. What is VL2? VL2 is 115 degrees. 115 degrees. Sorry, not degrees, 115 volts. So this will be 115 volts. Okay, then IL2 line current is how much? Already given to me is, that is 100 amperes. Line current is given to me 100 amperes. Okay, so magnitude of IP will be equals to 1 by 2, that is 50 amperes. So I can easily find out the magnitude of IP, but finding out the this voltage ratio will be a bit difficult. I mean, finding out the phase angle will be difficult. Magnitude you can find out, but phase angle, finding out phase angle will be difficult. Okay. So yeah, let's now solve the next question. So this is the next question. So three-phase questions will not be that difficult. Trust me, they will not be that difficult. But just few things you have to keep in mind. How are the supplies connected? What are the supplies? Those things you have to keep in mind, right? So this figure shows a delta star connected three-phase distribution transformer used to step down the voltage. Okay, from this 11 kV to 415 line to line. So it is a delta to star. So here I will have a voltage. I will copy this diagram. Can I? No, I can't. Okay. So it is still locked. So this delta connected side is 11 kV. Okay, delta connected load is 11 kV and the star connected load is 415 line to line. So it is from here to here, it is 415 line to line. If it has two switches S1 and S2, under normal operating conditions S1 is closed and S2 is open. Okay, so this is just a normal operating condition. Under special conditions S1 is open and S2 is closed. Okay, S2 is closed. If S2 is closed, that means the coil B, right, is totally short circuited, so no voltage will be developed here. Okay, that is the only thing that you need to keep in mind. In such cases, the magnitude of the voltage across the LV terminals A and C will be, okay. So they are asking in abnormal condition when S2 will be closed. So if S2 is closed, I will close it. It will be closed here. So here, right, actually here zero voltage will come. Zero voltage will come. Okay, and here how much voltage will come? This voltage is basically plus minus. Okay, this is open. S1 is anyways open. So if S1 is open, right, and I am directly applying 11 kilovolt. S1 is open because they have mentioned that when under certain special conditions, S1 is open and S2 is closed. So S1 will be open anyways. So I will just keep it open. So this will be 11 kilovolt. So this is they have not mentioned us any dots. Okay, that is actually a bad thing, but we'll assume a dot because anyways they are asking us the this magnitude only. So assumption is always this input side, this terminal, input terminal will be the dot and output terminal will be the dot for output side. Okay, that is only the assumption. Okay, so here I have 11 kilovolt that I am applying between phase AB. So this is plus minus 11 and this point is coming here. Okay, and the other point is open and this point is basically shorted. So basically, okay, just hold on. So these points are shorted here. So this point is automatically shorted here. Okay, this is also 0 volts only. This is also 0 volts only because it is totally short circuited, right? So ultimately only this voltage is getting developed here. Only this voltage is getting developed here. So am I correct here? Yes, you are correct here. Okay, why is this? Okay, this should not, I guess this should not be a dot. If this is a dot, then this will also be short circuited. Okay, something is wrong here. No, something is wrong. Okay, this should not be connected actually. My bad. This is not connected, right? Sorry, else everything will be short circuited. Okay, no. So here, right, actually something like this should have been there, and this also. Okay, so here also something is messed up this side. Okay, so actually this is not 0 volts, sorry about that. So this value, right, this will be this is open circuit, right? So this, right, this point will come here, and this point is here. What is this point? This point is basically short circuited through here. So this is actually minus plus 11 kilovolt, like this, minus plus 11 kilovolt. Okay, and this is the dot here as well, and this is the dot here as well. Okay, so if it is minus plus 11 kilovolt here, what will be the voltage here? I will calculate. So line to line, right, line to line is 11 kilovolt upon 415. So let me calculate the this turns ratio. So let me write down turns ratio. This will be N1 divided by N2. Okay, N1 divided by N2. So I can, like, if everything is normal, so for normal operation I will calculate the turns ratio, and it will be obviously same because transformer will not change, right? So turns ratio will be same only. So this transformer is delta star connected, right? So if it is delta star connected, that means here, right, the voltage will be same. It will be 11 kilovolt only. This will be 11 kilovolt only. Okay, so for normal operation it is delta star connected, right? So if it is delta star connected, in high voltage side the line voltage and phase voltage will be same, that is 11 kilovolt only. What will be the phase voltage in the low voltage side? So low voltage side is star connected, as mentioned, delta star, right? So low voltage side is star connected, so here the line voltage is 415, the phase voltage will be 415 divided by root 3. Okay, this will be equals to N1 divided by N2. So from here I can get the value of N1 divided by N2. That will be basically, if I calculate this value, this will be 415, 11,000 divided by 415 into root 3. So this comes out to be like 45. So N1 by N2 comes out to be 45.9. Okay, now let's come to this point, right? If I come to this point, I know that, okay, this is not 415 actually. I know this, that here I am applying 11 kilovolt. Okay, because here the line voltage, phase voltage is same. So what will be the voltage here? Voltage here will actually be 415 by root 3, right? This value will be not 415. This value will be 415 by root 3, but the polarity will be as shown here. Okay, and what is the phase angle? Remember, what is the phase angle? So this is what? This is simply the voltage VAB only. Okay, VAB only. So if I assume my voltage VAB to some value 11 kV angle 0, because the B phase is totally short circuited here and C phase is not connected. So this is also VAB only, but in opposite polarity, that's it. So here the angle will be, this value will be 11 kilovolt angle 0 degree, and if I go into the secondary, this also will be plus minus 415 divided by root 3. What will be the phase angle? There is no phase difference between the coil voltages. So 415 divided by root 3, this will be angle 0. Okay, so from here I can directly write what will be the values. So they are asking me to find out the value of V between voltage between the point A and C. Okay, so let me apply a KVL. So let me write here, this is VAC, right? Voltage between VAC, magnitude. So let me connect this A and C phase, and let me write this as minus and plus. Okay, so if I apply a KVL, this will be minus of VAC plus, remember this is also angle 0 degree only. So not this is, yeah, this is, sorry, this is not the one actually. This value will be what? This value will be, again dot is here, so 415 divided by root 3 angle 0, because phase AB has angle 0, that's why this also will be angle 0. So plus 400 15 by root 3 angle 0 minus, so if I come here, right, it is directly shorted through here, right? It is directly shorted through here. I don't need to go to here. I will directly go here. So it will be, I will come from here. I will encounter plus sign first. Then I will come here again. Again I will encounter plus sign first. Then I will end. So it will be not minus, plus 415 by root 3 angle 0. This will be equals to 0. So from here VAC VAC is equals to 830 divided by root 3 angle 0. Okay, what will be the magnitude? 830 divided by root 3, I have to calculate. So 830 divided by root 3 will be 479 something, 479 point something, right? So this will come out to be 479.2. So this will be the value of VAC. Okay, this will be the value of VAC. I hope you have understood this basic point. Okay, we did not draw any fancy drawing, and this was actually an unbalanced load question. This was an unbalanced load question. I did not use any formula, nothing. I used nothing. I just did the circuit analysis. So in GATE, right, question will come and it's a waste. Other students or everywhere else, if they have studied for somewhere else, they will just remember the formula and they will not be able to solve this question because they have just mugged up the concept. Have I ever used any formula here? This is just turns ratio. I have just simply solved the circuit, that's it. I have just simply solved the circuit, that's it. Understood? Okay. Okay. So let's now move on to the next question. So this is the next question. A three-phase, three-winding transformer. It is a three-phase, three-winding. So it's like a transformer bank. This is simply a transformer bank kind of thing. Okay. So it is a three-phase, three-winding transformer that is energized from AC mains 1.1 kilovolt delta delta star. So I have three windings. So sorry, a three-phase, three-winding transformer. Okay, delta delta star is energized from AC source. It supplies this load at 6.6 kilowatt and this load at this from the 400 volt winding. So actually, right, it is a three-phase transformer and it has three windings. What do I mean by it? So this is my primary winding that is actually delta connected. This kind of question we have not discussed previously, and I have three windings. So I will have one of the winding that will be again delta connected, and I will have another winding that will be star connected. So I'm just drawing the single phase equivalent. I'm not drawing the whole three phase line. Okay, so these are the three windings, and they're telling me that input side they are providing 1.1 kilovolt. So input side is delta. So if input side is delta, that because here it is written 1.1 kilovolt, that means they are talking about this side only, delta side only. So of course here the line voltage and phase voltage are same. So this value will be 1.1 kilovolt. Okay. What about here? So here if I provide a rated voltage 1.1 kilovolt, so in the secondary, in the delta side secondary, it will be 6.6 kilovolt. So this value will be actually 6.6 kilovolt. What about the star side? So in the star side I have 400 volts. So this value will be 400 volts. Okay. So how is the load connected? How is the load connected? So load here is connected. So it supplies a 900 kVA load at 0.8 power factor from 6.6 kilovolt winding. So this load is 900 kVA at 0.8 power factor. Lag. Okay. What about here? here it is 900 kVA, right? So this will be basically another winding is supplying 300 kVA load at 0.6 power factor lag from 400 volt winding, right? So given that the RMS line current in ampere drawn by the 1. So okay, they are asking what will be the RMS current drawn from the 1.1 kilovolt winding of the mains. So let's do one thing. Let's refer everything to the primary only. Because what I'll refer the loads, because what have they asked? They have asked the RMS line current in ampere by the 1.1 kilovolt. So what I will do is I will convert this. Let's say I have this 1.1 kilovolt transformer here. Okay, it is delta, I do understand. I will discuss about that. And here I will have two loads. So if I refer any load to the other winding, the kVA remains conserved, right? So kVA and power factor will not change. So if this consumes what is the 900 kVA, it will still remain same only. So this will be 900 kVA only. Power factor will be 0.8 only lag. Okay, and if this consumes 300 kVA, so the power factor will be same only. kVA will not change, 0.6 lag. Okay, voltage will change, I do agree, but kVA will not change and power factor will not change, right? So if I have referred this to the primary, then this will consume what from the winding 3, this will be I3 dash and this will be I2 dash. Basically this will be I1, and I know the line current and the phase current are same. Sorry, the line current and the phase current are different. So what I will find out is I can find this out, right? I can find this out. How will I find it out? I'll use the formula. So I know this is the line voltage across the two loads. I know this is the line voltage across the two loads. So what will be the line current referred to primary? So I know this formula, right? My S is equals to root 3 VL IL. Okay, from here I will be able to find out the line current because they have asked me the line current only. So this will be S divided by root 3 VL. Okay, so basically this value will come out to be, so what will be the line current of that second winding referred to primary? This will be 900 kVA divided by the voltage, that is root 3 into 1.1. okay, so this value will be basically, this value will be 900 divided by root 3 divided by 1.1. It comes out to be 472.377. 472.377. okay, this, yeah. Angle will be what? Angle will be minus, it is lagging, so cos inverse 0.8. okay, so this value will be I2 L dash, this will be 472.377 angle minus 36.86 degrees. okay, this will be the value. Now what about the other angle? Other angle is other current. So the I3 L dash, okay, this will be what? This will be basically S divided by root 3 again VL, this will not change, S3 this time. okay, this will be S2 here, this will be S2 and this was S3, that is only the difference. So this will be equals to S3 is how much? S3 is basically 400 kVA, right? So 300 kVA. So 300 kVA divided by root 3 into 1.1 kilovolt. So kilo gets cancelled. So 300 divided by 1.1 divided by root 3. This will be 157.46 amperes. What is the phase angle? Minus of cos inverse 0.6. Minus of cos inverse, this is 0.6, right? Not 0.8. This is 0.6. They have mentioned this is 0.6. So this will be cos inverse of 0.6. So cos inverse of 0.6 will be minus 53.13 degrees. Okay. Now what is the overall current? Overall current will be the addition of these two, right? Overall line current of the primary will be addition of I2 L dash plus I3 L dash. So this value will come out to be, I can easily calculate this value. This will be, okay, I have to do this, right? This will be 472.377. This will be 0.8 plus, sorry, minus j 0.6 plus 157.46 0.6 minus j 0.8. Okay, so this value, if I want to calculate, this is 0.6, right? This will be 94.476475 plus 2.8. This will be this will be minus here j, and this will be 126. Okay, plus 472.377 into 0.8. So this will be 377.9. 377.9. Trust me, when you will go and see the solutions, right, in the any PYQ book, you will see such a big calculation. You will see such a big calculation, and trust me, like no one will solve using this method. No one. So like you are learning the best thing. Okay, trust me on this. So this will be minus j. So here, right, 0.6 into 157.46. So this is 94.476, that is 48 approximately. So this value, right, comes out to be, so 377.9 plus 94 point, how is this so less? Oh, this is less only. Yeah, so this will be less only. Yeah, no, this one is, how is this so less, man? This one should not be less, right? 0.6 into 472. Yeah, I made a mistake. Okay, sorry. This will be 283.2. Yeah, now it is fine, I guess. Yeah, now it is fine. Okay, so this will be 377.9 plus 94.475. This will be 472.375. Okay, and what about the other one? This is minus of j. This will be 283.2 plus 126 point, okay, 0 only. So this will be 409.2. So this whole square plus 472.375 whole square whole under root. So approximately it comes out to be 625. Okay, phase angle also we can find out. Phase angle we have to find out, right? So phase angle will be 409.2 divided by 472.375 tan inverse of this, that is 40.9 degrees. Okay, minus, because it is negative, the imaginary portion is negative, so minus 40.9 degrees. That is what my current is, line current. So you will see in everywhere else, right, what will they do? They will use this, like they will solve here, they will find out this current, then they will refer it to here. Okay, in everywhere else. So this is the best method that you know. Okay, best method, least calculation. Okay, so whatever you are learning the best thing. Trust me on that. So let's solve this next question. So if the primary line voltage rating is 3.3 kilovolt star, in the star side the line voltage is 3.3 kilovolt of a 20 kVA transformer star delta, the per phase turns is 5:1, then the line current rating of the secondary will be. So they are asking me what will be the line current rating of secondary. So there are two ways to solve. Either you find out the line current rating of the primary and then you refer that to the secondary. That you can do. Or you can directly find out the line voltage of the secondary. From that also you can find out the line current rating. There are two ways. So I will solve using both ways. So first way is method 1, where I will find out the line voltage rating of the delta side. Okay, so how will I find it out? So I know that phase turns ratio is 5:1. So in the line side, in the star side, the line voltage is 3.3 kilovolt. So line in the star side is 3.3 kilovolt, right? What will be the phase voltage? Phase voltage in the star side will be 3.3 kilovolt divided by root 3. Okay, so now uh, what is the phase ratio? Phase ratio is trans ratio is 5:1. So this value I V phase in the star side upon V phase in the delta side will be actually 5:1, that is 5/1. Okay, so this will be 3.3 divided by root 3. So 3.3 divided by root 3 divide by 5 will be the V phase of the delta side. So from here I can directly find out what will be the V phase of the delta side. So V phase of the delta side will be 3.3 divided by root 3, 3.3 divided by root 3 divided by 5. So my V phase on the delta side will be 0.381 kV. Okay, this is the voltage on the delta side. Okay, now what about the current? So I know that the phase voltage and the line voltage is same in delta, so this will be VL delta. Okay, so I can directly write what will be the IL delta rated current. This will be S of the kVA of the transformer divided by the root 3 VL. So S is, it's a 25 kVA transformer, so this will be 25 kVA. 25 kVA is there and divide by 0.38 kV is there, so automatically kilo will get cancelled. So this will be into 0.381 kV. Okay, this value will be 37.88. 37.88. Now is there any other way to solve this? Yes, there is. So what we can do, this will be the answer, is we can find out the rated current in the primary and refer it to the secondary basically. So method 2, referring. So what is the rated current in the primary? So rated current in the primary, so I line in the primary, right, in the star connection will be S upon root 3 into VL. So this will be 25 kVA divided by root 3 into VL. So VL will be in the primary side, the line voltage is 3.3 kV, so it will be 3.3. So in the primary side, the what is the line current rating It is around 4.37 amperes, 4.374 amperes. Okay, now we need to refer this current in the secondary. How will I refer it to the secondary? So we know in case of star, the line current and the phase current are same. So this is actually the phase current only. Okay, 4.374 ampere. This is the phase current only. Now uh, what we need to do is we can do one thing, that I will refer it to the secondary. So I know the phase current ratio will be the inverse of the trans ratio, right? So I phase Y upon I phase delta will just be inverse of the turns ratio. So turns ratio is uh, 5/1. That will be inverse, right? This will be inverse basically. 1/5 will be equals to, I know what is my I phase star. I phase star is 4.374 ampere divided by the I phase delta that I need to calculate. Remember, it is the phase current, not the line current. Okay, so here my I phase delta is 5 times this, right? 5 times this will be 21.87 amperes. Now this is the phase current, rated phase current, but the in delta what happens, the line current is root 3 times the phase current. So this will be root 3 times the phase current. So root 3, this will yield me the same answer, that is 37.88. I will get the same answer. Okay, 37.88 is the same answer. Okay, now let's discuss few theoretical and interview questions. So what are the potential application and challenges of using a transformer deliberately introduce phase shift between its primary and secondary? Okay, what are the problems and applications? So a transformer is, if it is introduced to provide a specific phase shift between primary and secondary, it is used as a phase shifting transformer. Okay, why? Sometimes controlling power flow. So this, right, you will learn in PSA that if there is phase shift between the two supplies, then I can control power flow. Like the formula comes V1 V2 upon sine delta upon X, something like this. We will learn this when we will study power system analysis, don't worry. So by controlling phase shift means this delta angle will be controlled between the two supplies. So if I control this delta, the power flow will be controlled. So that's how we can control the power flow. Enhancing load sharing. So like if we can, I mean, by changing the phase shift, the load sharing also can be changed. Okay, if of course they need to have both, like if two transformers are operating in parallel, both of them must have same phase shift, but with overall phase shift, actually I can like enhance my load sharing. Okay, power factor correction is very important thing, because if I am able to, like already the loads are lagging, if somehow I am able to provide a phase shift of minus 30 or plus 30 or minus 30, whichever one is better, that will further get my goal, that is my power factor cos phi will be further closer to unity power factor, and I always want this, my power factor to be close to unity power factor, so losses will be less, so the actual current taken will be less. Okay, generating multi-phase supplies. Okay, this is one of the applications, we don't need to study this. And harmonic separations. Okay, so this phase shift is also provided for harmonic separations as well. Like if delta has, if the secondary high low voltage side has delta, then there will not be any harmonic currents, third harmonic currents in the line of the delta side, but in the phase there might be a circulating current, but in the line there will not be any harmonic currents. So sometimes these are used for harmonic separations as well. Okay, now what are the disadvantages? The disadvantage is managing this phase relationship provides grid operators with more control over directional power transfer, okay, and improves overall system efficiency and reliability. So we understood that, yeah, what are the advantages, but there are problems. So they are very complex in construction. If you see zigzag, right, so it is very complex, not that easy construction. So making it will increase the cost, and size of the whole device also will increase. Dynamic behavior under load. The phase shift may not remain always constant when the load is connected, right? Of course, we know, right, the terminal voltage is also not constant when the load is connected. it, although we say that it is almost constant because voltage regulation is very low, but still there is slight variation. Same here, right? Even if there is slight variation, again circulating currents may flow that can potentially like damage the devices. Okay, so now dynamic behavior under load. So the phase shift may not remain constant under varying load conditions, uh, potentially affecting the voltage regulation and system stability. Okay, so like that is what I just explained. Protection complexity. So traditional protection schemes may need to be adapted or replaced to suit the phase shift behavior. Okay, so we will not be able to protect it basically. Okay, so but additional protection mechanism are needed, which will obviously cause more, which will obviously cost more. Okay, harmonic interaction risk. If not properly designed, such systems can inadvertently introduce or magnify harmonic distortion. Okay, so we have to be careful because if we do not design it properly, extra harmonics can come. Although we are designing it for removing the harmonics, extra harmonics can also come. Okay, so another question is why proper phase alignment is crucial during transformer installation. Proper phase alignment ensures that the voltage and current are in proper phase sequence and phase angle. A misalignment or reversal can cause motors to run in reverse direction. So this we will learn in the DC motors chapter, not DC motors, induction motors. If phase sequence is changed, then obviously if it was supposed to rotate in the clockwise direction, now it will rotate in the anti-clockwise direction, which is obviously undesirable, right? So overloading of phases will happen if there is phase shift, if I don't properly align the phase. Okay, then we have this malfunctioning of protected relays, voltage unbalance and mechanical state. So these are mainly these are theoretical points that you should go through. Actually this was not supposed to be here, this was supposed to be here in the next page. Okay, now how does unbalanced loading affect a three-phase transformer? So if the load is unbalanced, first of all calculation will be very difficult, that is point one. Second point is there will be harmonics. Okay, we will discuss in the next chapter how there will be harmonics. There will be harmonics due to that if load is unbalanced, that means what? If load is unbalanced, that means the current in the phase A is magnitude of current in the phase A is not equals to magnitude of current in the phase B, and magnitude of current in the phase C. So these are not equal. If these are not equal, my magnetizing flux is also not equal, right, at every phase. So phi m, phi A is not equals to phi B. Is not equals to phi C. Okay, these will be not equal basically. So there is a problem. The core can get saturated due to unbalanced loading, and of course, if currents are different, some places it will heat up more, some places it will heat up less due to more unbalancing. Maybe IA phase A will be loaded more, due to that it can get damaged. Okay, these are the problems basically. Unbalanced load can be can cause uneven heating of the windings, increased copper and coal loss, potential core saturation, and voltage unbalance. Okay, so what are the mitigation techniques basically? So load balancing across all three phases, we can like at least connect balanced load so that there is no unbalanced. Use of phase balancing transformers if the phase are unbalanced. So there are few special kind of transformers. Okay, and we regularly monitor our system so that there is no unbalancing or harmonics. Even if there is harmonics or unbalancing, so then we will use phase balanced transformer. Okay, so that's it basically for this lecture. We did few interview questions, we completed those interview questions, and we finished our three-phase transformer with 2 lectures. Okay, everywhere else you will see that they are taking 10 lectures of three-phase transformer, and that much is not required. But you will feel, sir, only 2 lectures for three-phase transformer. The first lecture was actually almost around 3 hours long, and this lecture is also almost around 1.5 hours long. Okay, so yeah, this is enough. Trust me, this much only will be asked. We have solved gate POQs, we have solved ESC POQs, we have solved almost everything from three-phase transformer. So this should be more than enough. Trust me. So now we will come to the next topic. That will be the last topic basically, the open delta connections and harmonics in transformers. Thank you for watching, and I will see you in the next lecture. Until then, happy learning.